We are going to continue to analyze what is the relationship between molecules. Are they stereoisomers? If so, what type? Enantiomers, that's stereomers? Or are they something different entirely? Or are they constitutional? This is what we're doing now. So let's draw two compounds and let's determine what is the relationship. And here this is a cyclohexane. It is 1,2-dimethyl cyclohexane. And since we're here, notice that the two methyl groups are pointing to the same side. This is actually cis 1,2-dimethyl. I am incorporating the name, right? Cyclohexane. But I haven't said anything about configuration. Now let's see how is the relationship with another molecule. Now notice this is also 1,2, but no longer cis. This is 1,2-dimethyl cyclohexane. This one is cis. This is actually the opposite. One is pointing up, so in the wedge, and the other is going inwards, right? So if you consider that plane of the word, one is pointing inside and the other out. So they are opposite, they are trans. Right there, there's a way to determine the relationship. They are diastereomers of the type cis-trans. I also want you to notice something. When we analyze, the two molecules have two chiral centers, obviously. There's one here, same thing here. But we notice that the carbon on the top has inverted the configuration, but not the one below. So that was another way in which we distinguish enantiomers from diastereomers. So if we have multiple chiral centers, and if they're all inverted, then the relationship is enantiomers. But here we have one inverted, the other is not, so they are diastereomers. But also we know that that type of stereoisomerism cis-trans is diastereomers. So right there we have that. But also this molecule is interesting because it has something else. If you look at that, there is a plane of symmetry. We call that a plane of symmetry because say that dotted line, you imagine a mirror like this. So it's reflecting what is on top with what is on the bottom. So because of that, having that plane of symmetry, this compound has a special name, and we call that a meso compound. A meso compound, actually, the mirror image of the meso compound, and I'm gonna do that on the top, the mirror image, say, of this, like the opposite side, but they're actually the same. So when we consider the number of stereoisomers, and we know this formula 2 to the n, where n is the number of total chiral centers. Here in the trans, you have two chiral centers, and yes, you have two, so 4 stereoisomers, but we have, in the case of the meso, we have one less because they will be, meso compound is the same as mirror image, is the same as the original compound. So total, instead of having 4, so we have 2 here, this one in the enantiomer. And here, instead of having 2, I have just 1. So total, there are 3 stereoisomers. 1 pair here, that would be this plus the enantiomer, and here there's only 1. So when you have that case, then that reduces the number of stereoisomers. So it's supposed to be 4, but it's 3. Okay, now let's do one more. And let's say, having another example here. This molecule has a bromine here. And this one has a bromine here. So first thing, we have 1, 2, 3, 4, 5 carbons, 1, 2, 3, 4, 5 carbons. But I notice here that the bromine is in carbon 2, 1, 2, and this is in carbon 3. So the atoms, even though they share the same molecular formula, but they are connected different, so they are not stereoisomers, they are constitutional. Constitutional isomers. And not only that, the compound on the left, which is 3-bromo, and then you have pentane. So that compound is not chiral, because notice the carbon here in the center has attached this, has an ethyl to the side and ethyl to that, so that's not chiral. However, this compound is chiral and has an enantiomer. As it is right now, this is priority 1, 2, and 3. So this one is the S, and we only have one chiral center, so that's enough specifying that is 2-bromo pentane. So here we have done several things. There was an example of not stereoisomers. This were constitutional. This is not chiral. This is chiral. And above, we study what happens when one of the compounds, one of the stereoisomers that are possible, when one is a meso compound, that is, has a plane of symmetry. In that case, we have one less of the stereoisomers. Instead of having 4, we had 3, because this in the mirror image are identical. Okay, so we'll do more problems of that. We need to practice a lot this topic, determining absolute configurations, and work a lot in determining what is the relationship between molecules.